All right, first part of significant figures, we're going to talk about uncertainty in measurement. What happens when we actually go to the lab, try to measure something. We have to look at this and say, okay, how good are our numbers? So this is a graduated cylinder. Now suppose I fill it up with some water, and my water comes out to right about here. All right? So I look at that and I say, okay, how much water is there? The first thing you have to do is you have to read the bottom of a meniscus. The bottom of the meniscus is right here. Okay? That is the point where you want to read. Okay? So I look at that, and when I'm reading that, I look at the number and I say, well, it's between 15 and 20. Because this is a terrible graduated cylinder. I hope I didn't spend a lot of money on it. But I've got these separations right here, and I'm between 15 and 20. So what I know is that my value is probably around 17. Okay? So if I look at this particular measurement, I can say that that's about 17 milliliters. Okay, so this is a milliliter graduated cylinder. About 17 milliliters. Now if I go ahead and I put the divisions in here for, say, here's 16, here's 17, here's 18, and here's 19, okay? So I look at that and I say, all right, now that I look at that, I've got a little bit more than 17. It's a little closer to 18. Okay, I still don't have marks in there, so I can estimate what that value is. So now, that was reading A, okay, reading B, once I put those extra numbers in here, I can now say that's about 17.7 milliliters. Okay? On graduated cylinders, you may see smaller citations in there like that, and you say, okay, so I've got smaller, better identifiable marks. I look at that now, and now for reading C, I'll look at that and say, oh, well, I'm about 17.75 milliliters. Okay? Every time I do that last bit, that last little eyeballing of determining what my actual measurement is here, I look at that and I say, oh, well, if I'm eyeballing it, the last one, it's a pretty good estimation. The human eye is actually pretty good. But to characterize that nothing is certain in the world of science, what I'm going to do for each one of these and say plus or minus 1 milliliter. Okay, notice that's the last column for units there. For this one, it's plus or minus 0.1 milliliters. And for this last one, 0.01 milliliter plus or minus. Okay? So those are the ways that we read things. Now, how many significant figures does each one of these have? I'm glad you asked that question. It should be noted that if I'm reading a burette, and if you look at a burette, burette's this long thing down here. All right? The first thing that you should know is that burettes they have a number down here, 50, and they start up here at 0, and you fill it in from the top. Okay? If you actually are really good, and you fill this entire thing with base or acid, and you get the meniscus right on the 0 point, your initial reading should not be 0. Okay, that is not your initial reading. Your initial reading has more significance than that. Okay, because if you look at the burette does these tiny little gradations that are inside of there. So you look at that and say it's not 0. Okay, what you end up getting is a loss of significant figures if you actually say it's 0. My initial reading that a scientist would write down would be to say 0.00 milliliters. Initial reading, and the uncertainty would be plus or minus 0.01 milliliters. So that way we can describe how certain we are of that particular measurement, okay, based on how good our eyes are. Now, all of these numbers I've put on the board, all of them are significant. And why are they significant? But that's by definition, okay? Any number that we measure has to be a significant value. So each one of these terms is going to be a significant value. If those numbers are significant values, when I start doing mathematical calculations later, I have to hedge on the side of caution and say, I look at my significant figures, and the lowest number of significant figures is probably going to control the mathematics that are associated with that calculation. Okay? So the more significant figures you have, the better the overall calculation is going to be. All right? Yay! The lower number of significant figures you have, the more uncertainty that you're going to have with it. Okay? Now, once I have something with significant figures, I add up, or how do I know that something's got significant figures? How do I know the numbers inside are actually significant? Well, the first clue that you're going to have is if you have anything that's a non-zero number. Okay? So all non-zero numbers are significant. All right? So all non-zero numbers are significant. The first rule of significant figures. Okay? Good. All right, rule number 2, that zeros between non-zero numbers are significant. Okay, so that means that anything that's sandwiched between the two numbers. So if I write the number 705 here, I know that that 0 is going to be a significant value because it has a non-zero before it and a non-zero after it. Okay? Zeros trailing non-zero numbers after a decimal are significant. Okay? And the fourth one I'll put up here. Let's show you the example for these two. Zeros before non-zero numbers are not significant. But they do show magnitude. Okay? So they're non-zero and they do show magnitude. And let me turn this over. There we go. So now you can write those out. Okay, so here's example 1. So all non-zero numbers are significant. So if I have 75, all of those are significant. 2, zeros between. So if I write 705, the zeros between non-zero numbers are significant. The zeros trailing non-zero numbers after decimal are significant. So if I have 0.3810, the significant zeros are going to be these ones. So both of those are going to be significant figures. Okay? And zeros before non-zero numbers are still are not significant, but they do show some magnitude. So if I make this number even smaller, these two are significant. These 3 zeros are not significant, but they show us some magnitude. So if I say how many significant figures are in this term, the number of significant figures are 1, 2, 3, 4, 5. Don't include these. So how many significant figures are with 75 here? All right, 2. Good. So this has 2 sig figs. This one, 3 sig figs. How many for 3 and 4? Both of them are going to have 5 sig figs. Good. Okay, get a hang of this? Good. So I'm about to confuse you. All right, let me erase these guys. Actually, let me leave the burette. Okay? And now I'm going to write this number. 4100. There we go. 4100. How many significant figures does 4100 have? If I look at these two numbers, there's no rule for those. And the reason being is that this is not a case for rules. This is a case for they might be significant. Remember, in science, we're conservative, so we're going to look at this and say, I think those zeros, they're probably not going to be significant. I don't know, but I'd rather be safe than sorry. So I'm going to say that these two are not significant. So when I look at this number, I'm going to say that these two, this one only has two significant figures. These zeros, even though they're trailing significant, or they're trailing significant values, they may be magnitude holders. They may be showing magnitude, or they might not be. Depends on where the decimal is. Okay? Now, if I change this number and put a 0.0 there, at that point 0 indicates that I am expressing that all the numbers are significant. The position of a decimal, once I put that decimal there, that's an indicator that I have significance in every single value that I've got here. So this term, has 5 significant figures. Okay? Now, suppose I want to report this value and I go to my boss at the shipping yard and say, that container weighs 71,200 pounds. Okay, and your boss says, great, how many significant figures are there? Do I have 3 or do I have 5? And the scientist is going to say, I've got 3. And then the scientist looks at it and says, geez, I wish I had some notation that I could make this a little clearer. That's right, scientific notation is how we do this. All right? To turn things into scientific notation, what I do is I take the decimal, so the decimal will be here, and I'll move this 1, 2, 3, 4. Move that over, okay? And I express this as 7.12 times 10 to the 4. And what this means is that if any of these zeros are significant, if I put them here, it immediately recognizes them as a significant value by the rule over here. Zeros trailing non-zero numbers after a decimal are significant. This is trailing non-zero numbers after a decimal. So the scientific notation doesn't imply, it actually tells us that this is a significant zero. The other zero, not significant. So the only 4 significant terms in this measurement are there. Now let's go back to the example of the burette. Okay, remember the burette up here? If I used 0 to record significant values there, I've only given myself 1 significant value. Okay? If I do 0.00, wait a minute, which one of those is significant? Dr. Wayne, nothing's trailing a real number. I'm looking at the rules. My head is exploding. Oh! Yeah, you never thought you'd get that in a video, did you? Let's do it in close-up. So, if you get that 0, all right, and you measure it, if you actually measure the value, all of those terms are significant. So since this is a measured value, all are sig figs. Okay? The giveaway, once I put plus or minus 0.01 there, that indicates that I've measured that value. That uncertainty is a label that tells me, hey, I've got a real value here. Okay? All right, so let's do some calculations with these. And that'll be on the next video.